Morning, I'm Dan McCarthy with Munro Defense, and we're here at Aalo with Yaser to discuss work they've been doing on their latest generation reactor. And
Hey,
Yaser?
I'm Yaser. I'm the co-founder and CTO at Aalo Atomics, and we are building mass-manufactured nuclear reactors a reality.
So what are we looking at here, Yaser?
Yeah. So Dan, this is our full-scale reactor prototype, which we have built in our factory. The problem that we're solving right now is this large demand growth that we're seeing from AI data centers. I mean, if you think about how much power they're requiring, just in the United States, over the next 5 years, they want at least 40 gigawatts. Each gigawatt has enough power to power an entire city.
Yeah.
So that's 40 city worth of power, and the grid cannot handle that, right? So they want power 24/7, they want it reliable, but they also want it to be clean at the same time. And nuclear is the only technology that can provide all of those attributes. But the current challenge with today's nuclear is that, yeah, we can provide like gigawatt scale power with a large power plant, but it takes us more than a decade to build one, right? Whereas on the data center side, they're building these data centers within 1 to 2 years.
Right.
So that's a huge difference in time scale, right? And so that also introduces another problem. When you plan for 9 years and the plans take 18 years to build, there's a lot of uncertainty and the cost goes up.
Yep.
So really the speed and economics are the two biggest things that nuclear is currently struggling with. Unlike what most people think, it is not about the safety. Nuclear is plenty safe. We have a ton of data on that. And it's very reliable. It runs pretty much like, close to 95% of the time. So it's pretty reliable. When we want to bring in new technology, that's where the challenge is. So what we are doing in Aalo is, instead of building one large power plant, we're building smaller reactors. We're building hundreds of these in a factory.
Okay.
Right? So then the idea of factory manufacturing is not really new. Right? People have talked about factory manufacturing reactors since the 50s.
Yeah.
But why didn't it happen? If you look around, there are no factories like how we build rockets or cars that build nuclear reactors, right? And the reason is that large demand was not there that we currently see from AI data centers. That is what's different, right? So what we're doing in Aalo is, okay, we have essentially two products we're working on. One is the reactor itself, which is essentially this. And the second product is the factory. And factory plays a tremendous role in our overall business model. And this is our pilot factory. This is not a full production line just yet. We want to learn what it takes, what kind of equipment, what kind of people, what expertise level, what kind of rigging and machines that we need to fabricate and lift all this equipment up. So we want to learn as much as possible from our pilot factory line, where this whole facility is only 40,000 square feet, where we build one reactor at a time, right? But the goal ultimately is to take all this learning and build a gigawatt scaled factory. It sounds very much like a gigafactory, but it's called gigawatt factory, and there's a reason why that is.
Right.
Because right now,
Well, you're in the right city for gigafactories, but yeah.
I suppose so. But the reason why we call it a gigawatt factory is because our large-scale factory has to produce at least a gigawatt worth of nuclear reactor assets every single year.
Okay.
And if you think about how many reactors that is, each of our reactors can produce about 10 megawatt electric. So 100 reactors a year is our target from each of our gigawatt factories.
Okay.
And if you need more power, you build more factories, and it's the same playbook that every other industry uses to scale up something effectively.
And it's a single reactor, so if you need 50 gigawatts, you can just put 5 on site.
That's exactly right.
Yep.
So ultimately, we didn't go out and say, okay, what can we build in a factory, and how do we fulfill, and see where we can sell this product, right? we actually work backwards. We tried to say, okay, whose problem do we want to solve? And we said we want to solve the power problem of AI data centers. That's our first market. And what kind of unit power blocks would they want to see? Because if you think about a data center, they don't have a gigawatt scale building producing enough computing power. They have smaller unit blocks that makes up the overall data center site.
Yep.
So what does that individual power block look like for us?
Okay.
So we talked to a lot of data center companies, we saw what they were looking for, and ultimately we derived a product that is a convergence of what the customer is looking for, what can we build effectively in a factory setting,
Yep.
What can be economical, and then what is extremely safe. So
and what can be shipped to the site as well, which is another major issue in terms of the
we'll
size.
We'll talk about modularity and how we're approaching that.
Right.
But if you think about all those four circles and as a Venn diagram, the intersect is what we came up with as our product for AI data centers.
Yep.
We call it the Aalo Pod. So the Aalo Pod is a power plant that has a 50 megawatt electric turbine, and that's powered by 5 of our reactors.
Okay.
So 10 megawatt each reactor, they're all connected to a single turbine, 50 megawatt electric. Why did we do it that way? Because when one reactor is down for refueling, you don't shut down the whole plant.
Right.
You have at least 80% power being produced from the other 4 reactors, and producing, and still power the customers when they need it.
Okay.
And so when we need like larger amount of power supplies, we just copy and paste this 50 megawatt Aalo Pod up to a gigawatt or more, whatever the customer needs.
Okay. So, and they're all powering a single turbine generator?
Currently, yes.
Okay.
However, we're looking at, when you think about, okay, when one reactor is down, you can operate the other 4, and you can essentially bump up the power capacity to maintain the same power level. But what happens when the turbine is down?
Right.
Right? Because the turbine has to go through maintenance.
Right.
Every 3 years for a minor overhaul, or every 6 years for a major overhaul. During that 2 to 4 weeks time frame, you can rely on another pod. That's another option. Or we're also exploring with our customers of including a second turbine, right? So that one is down for maintenance, you can just switch to the other one and continue the power plant, and that's ultimately going to help provide this very high availability from a single plant that data centers would like to get ultimately for 24/7 power.
And the incremental cost of a second turbine generator is not huge
much compared to everything else.
Yep.
That's right.
Okay.
Yeah.
Okay.
So that's our product. That's our pod.
Okay. And now, from the manufacturing environment that you're dealing with, very different than stick-built reactors that are out there for a number of different reasons. But one of the biggest ones is the fact that you can control your quality much better in a factory environment. How are you dealing with working with the NRC in order to develop new specs that are appropriate for large-scale manufacturing?
Look, we require what is called a Nuclear Quality Assurance Program, NQA1. That's the quality standard that every nuclear reactor company has to follow.
Yep.
Whether you're building a stick-built project on site, or you're building a mass-manufactured nuclear reactor in a factory setting, either way we follow the NQA1. That's been the industry standard that usually keeps all of our nuclear reactors operating for 40, 60 years in a row. We follow NQA1 here in this facility as well. And you're absolutely correct. When you are trying to do a stick-build approach, the level of on-site work is tremendous, right? And whether
opportunities for errors are off the charts.
Weather gets in the way from each project to another. You get different set of skill set and people that you have to retrain. There's not a whole lot of learning you can transfer from one to the other. The benefit of working in a factory is that you have the same set of crew, same equipment, and you're just repeating and rinsing and repeating the same product over and over again.
Right.
So this is the what we call the Aalo 1 reactor, and the prototype of that reactor is what you see over here. It's about roughly 20 feet tall, and these are the internals of the reactor. You pick up the whole thing and you drop it in that reactor vessel, and we fill the entire reactor vessel with a coolant material that fills everything, all the void spaces. And that coolant is actually sodium, right? And I want to talk a little bit about sodium because that's really a key differentiator of how we do things differently from current reactors. And this is important to cover, right? So in a current nuclear power plant, and in fact, most people don't know this, 20% of our electricity in this country comes from nuclear power plants, and they all use what is called a water-based nuclear reactor. So, light water reactor technology is what it's called. Either it's a pressurized water reactor or a boiling water reactor. Either way, it's a pressurized system. You heat up nuclear fuel and the water takes that energy away. But as we all know, when water raises the temperature above 100 degrees, it tends to boil away. You don't want that to happen, especially in a pressurized water reactor. So what you do is you keep the whole entire system in a pressurized form to allow the water temperature to rise all the way to above 300 degrees Celsius, right? That's high enough temperature to create steam on the secondary side and drive a turbine.
Right.
Now, the downside of this is because it's a pressurized system, all of your vessels have to be thick-walled, all of your piping, and everything is pressurized. If you have a small leak, it will find its way until it drains the whole thing, and that's a bad day.
Yeah.
Right. And so you have to encase all of that primary system in a thick, concrete and steel walled containment, and that's what a nuclear reactor currently is. We wanted to simplify all of that down to very basic system structures and components. What we have done, instead of using water as a coolant, we use liquid sodium. It's a metal, but in its molten form, which has a very high boiling point, so it doesn't boil away. You can operate at high temperature and still maintain it as a liquid. And so everything is
at a low pressure.
Everything is operating exactly at low pressure, atmospheric pressure. Right. So all of our walls are very thin. Like for example, this vessel is 5/8 inch, and that's how much thickness we need for maintaining sodium at almost atmospheric pressure operating conditions.
Yeah.
And if you think about current water-based technologies, there's only one appropriate way of building them. Because they are large vessels and very thick-walled, you have to use forging. And forging for such vessels is very expensive, takes a very long time, and only few places in the world that can make it. So the lead times are 2 to 4 years for each one of those vessels.
Yep.
So huge bottleneck in the chain. So because we use low pressure system, we can make such a vessel not in 2 to 4 years, but in about a week, right? We roll thin plates and we weld them down, attach a flange and essentially a dish bottom, and that's how you get a vessel, just like this one over here. Right. This is built out of like stainless steel plates, and everything is low pressure. The way this machine works is very simple. Traditionally, nuclear power plants are what is called either a loop type design. Basically, you have a reactor vessel, bunch of loops to carry your heat exchange and pumping to other places, and you essentially have a bunch of pipes and loops going from the reactor vessel. The other type of a vessel is called a pool type design, where you take all of your primary coolant, instead of having multiple loops and multiple vessels everywhere, you integrate them into a single vessel. So all your heat exchangers, your pumps, your reactor core, all the support system, the controls of the reactor is inside one vessel. So this is closer to a pool type design, but one thing that we have done differently is actually a hybrid, right? Where interior of the reactor, we're acting like a loop type design. So we have dedicated piping from the pump is essentially drawing the fluid from the hot coolant from the fuel region, and it passes it through the intermediate heat exchanger, passes it down and back to the bottom of the core, and that circulation is what removes heat from the nuclear fuel that's sitting in the center, right? And as you can see over here, it's not a welded pipe. It's a pipe in a pipe concept.
Okay.
This allows us to remove components from the top of the reactor, so its maintainability is high. You don't have to go and break things up, and at the same time we're deliberately allowing it to leak because everything is dipped in a pool of sodium. So more or less it keeps the reactor what is called isothermal, right? You never want a nuclear reactor to have a localized hot zone. You want to keep it always at the same temperature.
Otherwise you get all kinds of stresses and
exactly
things don't go well.
Exactly. So we want to make sure the temperature is somewhat uniform. So having all the components in a bath of sodium helps it tremendously.
Okay.
So that's our pool loop hybrid design, and every component that needs to undergo maintenance or repair or replacement is on the top of the reactor. So if you want to replace a motor or a pump, you can do that without necessarily opening up the reactor. If you need to replace some of the heat exchangers, you can open up the top section and keep all the bottom of the reactor as it is. So it's not just designed to work, it's designed for operability, for optimal refueling on site, as well as maintenance and other activities.
Now, what is the life of the fuel? How often do you have to replace your fuel?
Yeah, so we're designing this reactor so that every 3 years we would take out 1/3 of the used fuel,
okay,
put fresh fuel in, and reshuffle the fuel assemblies.
Okay.
So every 3 years is our refueling cycle. But if you think about the residence time of each fuel assembly, it's 9 years because they're staying for 3 fuel cycles.
Okay. And what are you using as a fuel for this?
Yeah, so fuel is an interesting point. We are using the commercially available uranium dioxide fuel that is used to run all the commercial reactors around the world. The reason we did that is because the fuel supply chain is very mature, it exists, and as we scale up from one reactor to hundreds of reactors a year, we don't have to establish an entire fuel line to enable that growth. We can tap into the existing supply chain to ramp them up to produce our fuel, and it's already proven. We have 70 years worth of operational data from all the reactors, not in the US, but around the world. Regulators understand the fuel very well, and it's one of the lowest cost nuclear fuel you can buy. So from our perspective, it's a huge benefit. It's not very easy to use this fuel for an advanced reactor, which means a high temperature reactor, but we figured out a way how to do that in our design.
Okay. Now on the other side, you're using the salt. There have always been issues with salt as the cooling medium because of the corrosive aspects of it. I understand you've got some tricks that you've come up with in order to mitigate the possibility of leaks, which are obviously a major problem with sodium in air and water and whatever else. So can you share with us? You probably don't want to give us all the details, but a little bit. Okay.
So first of all, we use sodium metal in its metallic form. It is not a salt, so this is not a molten salt reactor. As a lot of people, when they hear the word sodium, they think it's a salt, but it's actually sodium metal.
Right.
And that's precisely why we don't use a molten salt, because the chemistry of molten salt has yet to be fully vetted out. If you think about all the advanced reactors that we ever tried as society, as humanity, right? Apart from water-based technology, which we currently use, sodium has the next highest experience level in terms of operational years. We have more than 400 cumulative reactor operational years with sodium-cooled reactors around the world. Wow. And that's a lot.
Yeah.
Because until you operate something for a large amount of a long time or large amount of reactors, you don't really understand the challenges operationally.
Yeah.
And sodium is interesting because it is one of the most compatible coolant to that of structural steel.
Really?
Yes.
Okay.
As long as you keep the oxygen content very low.
Okay.
And I can actually show you a device that actually keeps the oxygen content low. So
Okay.
let's go there. So this device is what is called a cold trap. This is what allows sodium to remain very pure. So any kind of a oxygen content in the sodium that may come from just the sidewalls, doesn't have to be present initially. There could be some hydrides in the coolant. So this device, essentially it takes a portion of sodium, cools it down, and passes through a series of filtration process that removes any kind of like material that's dissolved in the sodium, but can cause blockages in colder region of the reactor, which we never want. Cold traps have been designed and proven in other past reactors for quite some time. We didn't know anybody in the country who would make it. So we went and talked to a national laboratory, Argonne National Lab, who has a test loop. They looked at old designs and came up with a concept of how to build it. And then so we talked to those guys, and they're a fantastic group. And we learned how to do it, reverse engineered to what it would take to build our own cold traps. We designed, built, and tested these cold traps here in Aalo all over again. And these are the kind of technologies we need to make sodium cooled reactors work, right?
Okay.
There's another technology that I want to highlight, which is if you think about sodium, yeah, it's great with steel, and with this machine, we can keep the purity level very high, and we won't have any issues like corrosion or material buildup, and that's great. However, sodium is very reactive, right? So when it comes out, there's a leak or a break, it comes out and it can react with concrete, it can oxidize with air, and when it touches water, for example, it has a very violent reaction. And nobody wants sodium and water to meet. So because sodium and water is reactive, we want them to do the heat exchange to take the heat from the sodium loop to a water loop to drive a turbine to make steam, but we never want them to physically meet. So how do we achieve that? So over the years, many sodium cooled reactor programs tried different things. There's one technology that worked very well, and that is a double-walled shell and tube heat exchanger. Okay. It's rather simple, as it's it's a shell and tube heat exchanger. Instead of a single pipe, you have double pipes or double tubes.
Yep.
But the problem with the double tube is you have a large gap in between.
Right.
So you have a large temperature drop. Nobody wants that either.
Right.
So the best way to solve this problem is to have these two tubes snugged against each other with almost like minimal or no gaps, right? Yep. Or micron level gaps. Right. So let me show you how we have solved that problem. We have to go to the other side of the factory. Okay. So this heat exchanger, we looked around the country to see who would build or make this double-walled heat exchanger tubes, and nobody makes them. So the last time US built these tube-in-tube systems were 50 years ago, when we built the EBR-2 reactor, experimental breeder reactor in Idaho. That's one reactor that operated 30 years and did heat exchange between sodium and water with no issues, right? So let's take you to the other side of the factory to show you how we have solved it. We went and actually found a company that would partner with us on this new and novel way of heat exchange. And this company is awesome because they're really obsessed about making the best tubes or pipes. And so they have multi, 500,000 square feet facility where all they do is make pipes. And they got really interested in what Aalo was doing because we can essentially solve the energy problem that the world is facing right now, and they wanted to be part of it. So we worked together and figured out how to make these tube-in-tube heat exchangers, and they essentially would manufacture the tubes, and we would bring the tubes here and manufacture our steam generators. So if you look into here, this is what the ultimate tube-in-tube for the heat exchanger looks like. You can almost see like a very faint line between
I
the two
think
tubes.
on this one you can see it a little bit better.
That's exactly right.
Yeah.
And this seems simple, but it's very hard to achieve.
Yeah.
Right? You almost have to draw both of these pipes together at the same time.
Yeah.
Right? And these guys can mass manufacture these, can scale as we need it to. And this is a prototype a heat exchanger. So essentially our full-scale reactor will have double the amount of length, as you can see over here right now.
Okay.
So yeah, so technologies like this is what's needed to build a true sodium-cooled reactor power plant, right? We can't just like say, hey, look at our beautiful design on paper and PowerPoint. You know, you have to be able to work on these key technologies that solves each of these problems that we have had in the past. Another issue is, how do we go about solving leaks, right? So when you have, the primary system, we don't anticipate any leaks because, it's in a big giant vessel.
It's all
and
internal,
we have another vessel around it.
Right.
So if one vessel leaks, it still has a catcher, and the core never loses its coolant. It can naturally remove the heat, and that's not an issue. But our secondary loop is also a sodium loop, and that has pipes and vessels and heat exchangers and a lot of welds.
Okay.
And we can have like some of the welds fail over time, right? In the past, that single-handedly was the reason why sodium-cooled power plants stayed down for a very long time.
Yeah.
And the reason is sodium is reactive, so when there would be a leak, people wouldn't go in because it would create sodium oxide fumes. That's not good for the health. So they would wait and let it burn away completely, and then they would come in and patch it up. And that could take like months.
Yeah.
You don't want your power plant to be down
No.
for months.
No.
So what we have done is we've actually designed a sodium repair robot. I mean, we live in a different times than 50s and 60s.
Right. Yep.
So we have a remote control robot platform that can go to a plant, and then we have access in X and Y and Z direction.
Yep.
So this platform can move around in the plant, and then and that's manually done, right, remotely. Well, once you reach to the spot where you have the actual leak happening, we have a machine learning robot that can detect where the actual leak is happening and do a welding repair, in situ, using AI ML to do a perfect weld. And then so people can go in later and do a proper weld on it. So it really prevents a situation where you have to wait months to wait for people to come in and repair something. Right. And that's one technology that will help this plant stay online longer and achieve a high capacity factor.
Now, is this a robot you developed, or is it a?
There's multiple robotics going on here.
Yep.
We basically have three different platforms. One platform that locomotes that we are remotely handling, those are available systems, right? That's off the shelf. The plugging system that I cannot disclose what technology that is, that patches it up on a sodium leak, that we have designed internally. The AI ML system that would detect a leak and actually have the nozzle move over to do the leak repair, that we have designed internally. And so it's part off the shelf and part our innovation that's making this technology come to life. Yeah. As you can notice here in this factory, there isn't a whole lot of different types of fabrication machines. There's only like 4 or 5 types. And the reason is, when we had our original design, we hired a bunch of folks from other industries like automotive, aerospace, oil and gas. So we hired a lot of folks from SpaceX, Tesla, Neuralink, Boring Company, and the Houston Oil and Gas Company. People that have built stuff, right? That comprises our manufacturing team. And we handed them the design, and they said, well, this design is great from a nuclear perspective, but it's not the best design for manufacturability and assembly.
Yep.
So we actually worked with you guys, Munro, for our first iteration of that design to take what our engineers have come up with and make it into a DFMA system, right? Designed for manufacturability and assembly. And that assessment kind of like gave us the glimpse on like what kind of equipment, what kind of machines, what kind of resources we would need to make these systems, right? And that was eye-opening for us.
Right. And that was at INL before you moved from INL down to Aalo.
Did we work on Aalo, to be clear with you guys?
Yes. Yeah.
Yeah, we did. Well, we worked with you guys for multiple stages, right?
Yes.
Okay.
Yeah.
I'll talk about all of that INL stuff later.
Okay.
But so when we took the DFMA design, and then so we looked at the equipment internally, we went through another layer of DFMA, which is how can we redesign this so we have fewest amount of machines that we need to fabricate the reactor. And that gave us like, we need a bandsaw, a water jet, CNC mill, lathe, press brake, a VTL. These are only few machines that we can buy off the shelf to build our reactor. We don't have to custom design a bespoke fabrication machine.
Yeah.
And that was a huge plus.
Yep.
And in building our reactor, it's welding. So we don't automate a whole lot of stuff, but anything related to welding, we thought is a great area to automate.
Yeah.
Right.
Now, does the NRC recognize automated welding? Because I know in some, like the defense industry, getting them to buy off on automated welding, which obviously is a much higher quality weld.
Right.
But they haven't been doing it for 50 years, so who knows if it works, although you've got plenty of data that says this is a lot better than having people do it.
That's right.
Has that been an issue getting that process certified for you?
Yeah, so the way an NQA1 nuclear quality assurance work is more than how you did the welding, they care about how the inspection works out.
Okay.
So for example, if there's a component that has a safety function, the quality requirement is such that you have to inspect the weld
360
100% of the weld for that component.
Yep.
Not 5% or 10%, 100% with one method, and like ultrasound, X-ray, dye pen, and then use a completely different method, do it all over again. So you inspect the weld, 100% of the welds that has a safety function, right? Yep. And so whether we do it by a human or by a machine, we can get to the same endpoint, right? So obviously you can buy. I'm gonna tell him to pause for a second. So one of the major areas where we thought we could automate is actually welding. We do tens and thousands of linear feet of weld. Yeah. And so obviously you can buy automatic welding machines off the shelf. They cost like $500,000 or $1 million depending on what kind of a machine you want. So we can do that, but it's kind of costly. Yeah. And we're all about cost reduction, even for our first of a kind. So our team said, well, let's try to do it internally. And so they have put together using like, scrap parts that's worth like $70,000 and actually build a track-mounted TIG welding system that is at a fraction of a cost that you can buy from off the shelf. And they even qualified that welding from that machine. Okay. And it just does perfect welding that would meet our NQA1 standards in terms of inspection purposes. Yeah. So it's a beautiful solution. Yeah. So when we go from here to the gigawatt factory and we need to hire 200 welders, maybe we need like 20 welders and then copy and paste these systems like 10, 20 times to kind of have humans overseeing what the robot welding is doing. Yeah. And so we don't have to have manual workers, doing welding 24/7. We can have machines do the hard job and the humans being the supervisors to those operations.
And it's nice, everything is round.
Everything's either round or straight line, right?
Yeah, yep.
And if you think about vessel fabrication, that's the two things that we need to achieve. So I'll show you let me show you where the setup is, it's going to be mounted on top of that platform. So it can move on the track mount for linear welds such as this. Manually, this takes about a week for a manual welder to go and weld this 5/8 of an inch thick stainless steel plate.
How many passes would you?
When I ask this answer, like it's more than 15 passes.
Okay.
Right. So a lot of passes to make this weld happen, and it's very tedious.
Right.
And you have to have 24/7 multiple shifts to make this work fast. So having it automated saves huge amount of time for us. So you mount the system on top. So anytime you have to do a linear weld, you can do that. Anytime you want to do a circumferential weld that involves like connecting two rings, you can allow the automatic tank rollers connected to the welding system, so we can deposit the weld as it turns the rings, and that allows it to automate the process.
Yep.
So again, vessels that normally takes 2 to 4 years for pressurized nuclear reactors, that happens from water-cooled system or gas-cooled reactors, we can do that in about a week or less.
Wow.
Pretty cool.
Yeah.
So yeah, that's all the work.
Okay. And this is all 316L?
This is
Or
all
is it-
316L.
Okay. I was thinking temperature-wise, you're getting into the 316 H range, but
we
can
started
keep it-
using H,
Yeah.
but the challenge with H is, the heat-affected zones.
Yep.
You have at the welds, you essentially, cannot, because of carburization that happens at high temperature. So you have to almost do solution annealing of the vessel after you weld something to make sure that you get the fine grain structure.
Yep.
So that becomes very costly and
Yeah.
expensive
No,
and
if you can
tedious.
stay away from the H,
Yeah.
that's great.
We are trying to stay away from H,
Yeah.
but we lowered the temperature a little bit to make sure that for 40 to 60 years of operation, the L grade can operate just fine.
Okay.
I think when you think about the economics, it seems counterintuitive, but lowering the temperature, you're going to take a few hits in efficiency on the turbine side.
But lifetime is going to be
But the lifetime is
yeah.
going to be significantly extended, and it's much easier operation, lower cost of the reactor overall. So we actually get more juice out of the system for longer with a
Yep.
lower cost than otherwise, right? And that's the benefit of doing using a techno-economic model to allow you to make decisions on the technology side.
Right. Which is probably a rapid or a major paradigm shift from previous nuclear design activity, where it's all about power output.
That's right. That's right.
And
Yeah, and there's a lot of like, so if you think about this factory operation, it's all physical here, but there's also a digital side of it, which we haven't talked about. The digital side, basically tracks all of the inventory management, supply chain management. You have your manufacturing execution system, and you have all the data that we're collecting in building our first reactor, like how long it's taking to build a particular module and whatnot, and how much consumable we have used, how much welding time, what kind of equipment, how much floor space. All that data we're getting from the field from building the first reactor, right? So we're also working with some of our hyperscaler partners with their best AI teams, where we are building an AI agent that can take all that raw data from the first experience from this pilot factory. And so if we want to go and build out, let's say, hey, I want to build a gigawatt factory that spits out 200 reactors a year, right? How big of a floor space do I need? How many welders and machinists do I require? What's my total staff? How many number of water jets do I need? So these all can be done by humans. It'll just take a longer time, but the AI agent can give you rapid answers very fast about the optimal design of that gigawatt factory. So we're also like playing with some of those newer tools to go through decision making faster and be able to deploy at a scale that we haven't seen in nuclear.
so you're not tens of thousands of people here.
That's
You're
right.
you're taking on a lot of new technology investigation to try to basically look at all the different aspects of making you successful. What size is Aalo right now?
So we're about full-time people, about 100, and we have approximately around additional 50 in our consulting companies that we rely on for work activities that are short-term. We don't need to like hire them for forever, right? But whoever we have hired, we are very selective. We make sure that anybody that we hire for a particular role, they are the very best in the country in that particular role. So we, less than 1% of the people who we interview or who apply to Aalo is actually part of the team. So we're pretty selective.
Mm-hmm. You mentioned it's managing your supply chains as well. How has that been going in terms of developing robust supply chains, and do you need to have all of your suppliers US based and material US based?
We maximize the US supply chain as much as possible unless we don't have suppliers in the US, then we go lean on other countries. For example, turbine. We have partners who are working out of Europe, so we can get turbines from there. Some of our sodium material comes from France, but majority of the components we're trying to keep it US based because we want to have US manufacturing be first. We want to ultimately vertically integrate. Right now we're relying on some partners to get some components and parts, but ultimately we want to be able to do it ourselves and vertically integrate. But when it comes to supply chain, and that's probably one of the most essential areas to focus on, because if you don't build enough of something in the country, you don't have suppliers that you can rely on. And so for the last 2 years, even though we're a small company, we've been really focused on getting our supply chain mature. So we reached out with a philosophy of 3 things. When we reach out to our partners, we say, you're an ideal partner if you can provide components at a certain price, at a certain quality, and you can scale as we scale, right? So you have to have that appetite. But right now our philosophy is anything that is a commodity, that is the idiot index is very, very low, right? We don't want to go and manufacture those components. We want to rely on suppliers as long as they comply with these 3 criteria. Everything else, we want to be able to build ourselves.
But there are a lot of exotic materials that go into the reactor that have limited production in the US at this point in time. Is there anything being done to develop that capability that you're aware of being pushed? I know the administration has looked at freeing up the ability to extract materials in different locations. Is that helping you out, and are some of the key materials that you need included in that activity?
So look, our philosophy has always been, we don't want to have any unobtainium in this reactor power plant, right? So we want to make sure that we select technologies that we have available supply chain of. Even though something might look better on paper, but in reality there isn't a supply chain. That's unobtainium to us. So when we design this reactor, we make sure that we either have a pathway to buy from current supply chain, or we can build it ourselves. So we don't have any unobtainium right now in this reactor, including fuel, right? There's a lot of some of our peers in the industry, they're using different types of fuel type. We're not pursuing any of those. We want to use traditional off-the-shelf nuclear fuel that runs our current reactors reliably. We want to be able to use that and all common materials we can find in supply chain.
Did you investigate the use of TRISO at any point on this, or?
We did. I'm very familiar with all the fuel types and the pros and cons of each. The reason why we did not go towards TRISO, obviously supply chain.
Very
the cost
expensive.
is very high. And when you end up solving those 2 problems and you build a reactor, the physics works against you because your power density is very low, right? So what does that mean is from a same core, if you have a meter cubed volume of a core, the maximum you can extract out of a TRISO fuel reactor is 5 to 6 megawatt per cubic meter. For current commercial reactors that we can find everywhere, that's about 100 to 200 megawatt per
huge
cubic
difference.
meter. Huge difference, right? So we want to be able to not be that low. We want to make sure we have a technology that has a very high power density, because the core is big. If the core is big, then your vessel is larger, your shielding is more, your building becomes bigger. So everything kind of follows how big the core is. And we didn't want a super large core for our reactor.
So what kind of time frame are you looking at from beginning of site prep to turning the switch?
So for our first prototype, we're essentially doing it in less than 12 months, but it's a single reactor, a small turbine. For actual power plant, it'll be 5 reactors and a bigger 50 megawatt turbine, and all the bells and whistles that go with it. Ultimately, our goal is like we can deploy, half a gigawatt or an entire gigawatt in less than 12-month time frame. So for a single pod, from the time a customer orders saying, hey, Aalo, we need a Aalo pod from you guys, and by the time we provide electrons, it is done within less than 12 months. And that includes all the licensing, supply chain readiness, financing, the on-site construction, the manufacturing, supply chain, aligning all the long lead procurements. That's not very easy to do. In fact, most people will say that it's too audacious, not possible. But that's the goal we're trying to work towards. And if we can achieve that 12-month time frame, we're going to be at the same scale as building a data hall.
Right.
For data centers.
Yeah. And versus 30 years?
Versus 10 plus years for a gigawatt scale plant, right? So it's only it's a two-step approach for our reactors. We want to be able to deploy very fast in factories. So the factory, how we design the factory solves that problem. But we need to also work on how quickly we can deploy them on site and do everything that's needed to turn the machine on, right? So those two will help us achieve both the speed and economics that we're trying to solve.
So, Yaser, it's been great seeing you again. I appreciate your inviting us out. And so this is Munro Live, signing off from inside the factory. We'll be talking to you a little bit more, a few more questions that we've got that we'll add in at the end of the process.
So you guys started working with Yaser even before Aalo, right?
Yes.
Yes.
Yeah.
Yeah, when Yaser was back at INL was the first time I engaged, and one of the other associates that we had did a smaller project, and then we got together working on looking at the techno-economic model and looking at the design, going through design simplification, and it was I'd say about a 1-year activity that we spent going through it. So it was an interesting project.
Yeah,
and
totally.
There's been a lot of improvements since then as well.
So when we were building Marvel, which is a test microreactor at the INL, it was not meant to be mass produced in any way, but it was supposed to help us tackle some of the challenges that microreactor would be solving. So we thought, hey, we've got a design, what better way to figure out what's needed to mass manufacture these? So instead of just going and building a bunch of them, let's go try to, do an assessment. What would it take? So I knew about Munro from before I even joined INL, and I thought, let me reach out to them. And we started working on a project saying, okay, here's a design. If you were to manufacture hundreds of these, how would you do it? And what kind of impact it would have on the design? And that experience was very eye-opening to me, right? Because you guys came in and you're not like, doing this, right? You actually have an analytical method to look at the entire bill of material, the BOM, the CAD, and look at every single parts and pieces, dissect them down and see how are we going to either buy them or manufacture them, what equipment. So you lay out the entire process, what would be the foundation of building a factory. So when when obviously I moved away from INL and, worked with Matt to start Aalo, we thought, okay, that is certainly the first step that we need to take before we even build a factory. Mm-hmm. So we called up Munro and said, hey guys, help us again. And that was really good because we had a design that was originally done by our design team, which they thought they had designed for manufacturability and assembly done, but in reality, we didn't do a very good job, right? So when Munro came onto the team and pointed out all these like 13 or 15 different improvements, that's going to massively change either our time to manufacture or bring down the cost or the number of equipment that we would need, to build a factory, that was very eye-opening to us, and it was super useful. And we learned from that initial work, and we're essentially baking DFMA as part of our work almost in every design cycles.
Yeah, I think it's worth highlighting, at that stage, we were a 2 to 5 person company. So we were working out of a WeWork at the time.
That's right.
And we had a lot of great ideas around how to design this reactor, but less prowess on the team at the time around how to mass manufacture it. So Munro was super helpful at coming up with a plan and ideas there that we could talk to investors about and say, hey, look, it's not just the reactor that's the product, the factory is the product. Right. So you guys were a huge help with that.
Yeah, and that's great. And yeah, so industries like nuclear and whatnot, you get a lot of PhDs involved that tend to be a little bit more removed from the manufacturing floor and are getting into the physics. So it's a good partnership, because I certainly wouldn't want to try to design what fuel you're using or any of that stuff. That's
right. And I think we continued that. It's really the mindset adoption that's really the key, right? So when we did the original project with Munro and we started hiring people from SpaceX, Tesla, Neuralink, Boring Company, the oil and gas sector, and we brought all these people together who have built things. They already have that ingrained in their brain of what a proper design would look like for DFMA, right? And they brought in that next layer of DFMA feedback from their experiences. And so we're essentially building, learning, iterating, and making improvements, because when we built the full-scale prototype, which we just saw, we thought we had DFMA done. And what turned out was we found out that we did a pretty good job at DFM, design for manufacturability. But when we tried to assemble it, we did it super fast, like 2 weeks we were done with the whole assembly. But it was very challenging. And the design engineers were involved in that process. They took a step back and said, I think we need to change the design so we can assemble it faster, so we don't have to live with such high tolerances. So that also gave us a lot of insight. So until you build something, it's very hard to really understand, okay, I've done DFMA, but have I truly achieved it?
Yeah, and you can map it out looking at the assembly process and make some assumptions, but until you have those physical parts in your hand, some are more difficult than others. I do recall one issue in the original design where we were lifting everything up and trying to do a blind made of a spring mechanism in the top, and that was like, this is going to be not a fun job. Nobody's going to want to do this. So, but
a lot of small innovations that went to make this whole product come to life.
Right.
Yeah.
What we're doing at Aalo is essentially mass manufacturing nuclear power plants, and really the exciting thing is there's never been a time like this for nuclear really in the entire 70-year history, right? And so in the first atomic age, there was a pretty rapid build out, but it was kind of for bespoke projects that were very much government-led, and these were kind of one-off reactors. And right now we find ourselves in this time where, yes, there's record levels of public support, of government support, of investor support, but most importantly, there's a huge amount of support from the right customer. So AI data centers, they're presenting 40 gigawatts of demand in the next 5 years. And that's like creating 40 new cities in a 5-year period. And the last time that happened was never. So this is insane. And they also have a very high willingness to pay, right? So they actually value speed.
Right.
That's what they want. And they're willing to pay a premium. And so it's really this incredible opportunity where you can set up this nuclear gigawatt factory and come down a cost curve and then go after all these other markets thereafter. So, kind of similar to how, for example, Tesla started with the Roadster, then the Model S, then the 3. We're starting with this product that's a really beautiful fit for data centers. And, don't get us wrong, it'll be more expensive, but it'll be way faster and really well suited for data centers. And then once we come down the cost curve, there's all these other markets where suddenly at that lower price point, it opens up actually entirely new applications. So for example, smaller municipal utilities, for them, they don't need a gigawatt scale plant.
Right.
But once you come down the cost curve, they could actually use a 10 to 100 kind of megawatt product. Mm-hmm. And similarly, desalination, industrial process heat, that's a big one that nuclear has long dreamed of servicing, and there's really only one example maybe globally of that being done at industrial scale. And then eventually we actually want to go after developing nations. So bring the cost low enough to bring a lot of the world out of energy poverty. That's our overall mission. So
there's also within the military, forward operating bases would be a potential good market too, because one of the most dangerous jobs in the military is the diesel fuel truck driver, which or an XMR. An XMR would handle perfectly, it seems like, as well. So another market, it just seems like the markets are pretty much endless.
Yeah, on the defense side, it's not just the forward operating base, but there's a lot of critical infrastructure that you want to continue powering that today are relying on grid power, right? They're not moving, they're just stationary, but they are required to, get the power from the grid that they are, living around. So. But if the grid is down, they have maximum 2 weeks of backup power. But imagine if you have an XMR, like one of our products, for example, be there, you can have at least, for an entire fuel cycle, 3 years worth of time where the power does not have to go away. Now, all of a sudden, you can have decentralized generation in each of these critical infrastructure that's powering, defense or mission critical functions that does not have to rely solely on grid power, and you can have continuous power for even if somebody takes the grid down. I think that takes us to a completely different level of resiliency we have not seen before on the defense side.
Yeah, and there's probably going to be a lot less resistance to data centers in local areas too, because they're all concerned about their electric rates skyrocketing because they're going to, the demand is going to go like this and the supply is staying here. There's only one thing that's going to happen. Prices are going to go up. So if you can fill that gap, they can land data centers with much less resistance in the community.
I think this will actually kind of flip, and there'll be a bit of YIMBYism, yes, in my backyard for what we're doing. Because, to your point, it's this whole new model of, essentially on-site generation. And in doing so, people don't often realize, the cost of generation has actually come down a lot in the past 20 years, but the cost of transmission has gone up. So overall, power costs have gone up, and the grid is getting fragile and old. And so if you can bring in this on-site power, especially if we're now talking about going from a gigawatt on-site, maybe even to 5 or 10 gigawatts, I mean, that's crazy. That generation, like you said, is just not there. So if you do this on-site and then you sell your N+1 energy back onto the grid, not only are you not a bad neighbor, you're a good neighbor. You're strengthening the grid, and you're keeping costs down. And with our technology, you don't actually need water either. So that's another big challenge. So for all the hyperscalers, the main pushback is from local communities is the air is going to get dirtier, you're going to destabilize the grid, you're going to use a lot of water. We solve all three in a package that can be deployed super quickly. So it's insanely exciting, and it's a race to pull this off.
What time frame are you thinking that you'll be launching or landing your first unit?
Let's come back to this question, but I want to add one more thing to the previous thing. So right now, if you look at AI data centers, the reason why some of the people don't want data centers is because their rates would go up the way you said. And that's because data centers don't have any other alternative, because they want to have 24/7, 999 or 59 reliability. And without the grid, they can't have that reliability with just on-site power. So when we are thinking about how to solve that problem for the AI data center with our N+1 configuration of the pod that we talked about earlier, then only then can a data center company can say, you know what, I actually don't need the grid for backup because I've got enough redundancy on my on-site power. That's running 24/7. I'm getting 99.9% availability. I don't need to impose on the grid and its customers to make my data center work. Right.
And upgrading that grid is just, trillions. It's
exactly
massive investment throughout the country.
When we can truly have our customers tether from the grid and provide them reliable power, behind the grid, that's when we truly solve the problem for AI data centers, right? And I think our product is gearing not for problems of data center problems today, but they're problems that they're going to face that will help them tomorrow.
Yeah. Yeah, and so our thought there is, we still want the grid interconnect to happen because we want to sell the excess energy back onto the grid, be a good neighbor.
Yep.
But the reality is we can actually deploy faster than many grid interconnections can happen.
Exactly.
So that's the differentiator.
Yeah.
And I've got to run in a minute, but so our goal here, we are on track to achieve criticality by July 4th of next year. So that means turn the reactor on for the first time. This is super exciting. Next year, we'll also be beginning long lead procurement on our gigawatt factory. So what you guys toured today is the 40,000 square foot pilot factory. We're going to be setting up a factory at least 500,000, maybe 1 million square feet to output several gigawatts per year of capacity by 2030.
Okay. How is your fundraise going for being able to take care of all that CapEx that you're going to be pouring into that plant?
Well, we're constantly fundraising. So if there's any investors out there, please reach out. But we've done a good job so far. So we did a 6 million seed in year 1, 30 million Series A in year 2, 100 million Series B just a few months ago. So the capital is there for the companies that can execute really well. So we're doing our best.
Yeah, and so far we've executed, even though we're a small company, we've achieved things in this last 2 years that a lot of our peers have not achieved in 10 years. So we're executing fast. We don't take shortcuts. We're trying to hit every milestone, but significantly shorter timeline. And that's allowing us to get to market faster and be able to provide a solution to what a lot of these AI data centers are looking for.
Yeah, there was quite a few impressive things that you've got going on out there to take care of some of these long-standing issues, which is key. So.